Hi class, welcome to Refrigeration and Air Conditioning Lecture 4 on Psychrometrics. So the definition of psychrometrics is it's the science that deals with the physical and thermodynamic properties of gas vapor mixtures. Okay, and in the last class I had mentioned we'll talk about humidity in the psychrometrics class. That's because psychrometrics is primarily concerned with the mixture of air and water vapor. Okay, so humidity is one of the primary discussions in this topic. The to understand the behavior of a gas mixture involving uh, a gas and a vapor, in this particular case, mixture of air and water vapor, we do need to understand a little bit about the behavior of gases. Okay, so for that purpose, let's start with the differences between ideal gas versus real gas. You've all heard about ideal gas uh, earlier in your thermodynamics class or even in your physics class. Um, it's basically, or even in your chemistry classes before. It's basically um, the gas that obeys PV equal to nRT law, where P is the pressure, V is the volume, N is the number of molecules or number of moles of the particular gas present in that volume. R is the universal gas constant. T is the temperature in Kelvin. So any gas that obeys PV equal to nRT for a certain range of condition can be considered as an ideal gas within that range. In reality, most gases or almost all gases are non-ideal gases, but they could be considered ideal gases in certain conditions under certain ranges. Now, what are the other properties of ideal gases? For a gas to behave like an ideal gas, it's essential that there is no intermolecular forces of attraction or repulsion between them. Only thing that happens is just collision between the molecules, okay? But there are no intermolecular forces present. The other important thing is such type of gases do not exhibit phase transition. In other words, such type of gases will not become liquid even if they are compressed or cooled to really low temperatures. Because the essential feature or essential property that causes the gas to condense is the intermolecular forces. The absence of intermolecular forces means the molecules within the gases cannot combine to condense into a liquid. Now, the actual gases or the real gases deviate from this law, right? This is especially true when the pressures are high and when they are cooled to low temperatures. So instead of the typical um, ideal gas law relationship between pressure, volume, temperature, and number of moles, the relationship for determining the state of the gas uh, needs to account for intermolecular forces, and then there are several types of such relationships proposed. Um, some of which are van der Waals equation of state and Peng-Robinson equation of state. For example, in the van der Waals equation of state, it's somewhat similar to what I'm going to write here. It is P plus 8 by small v squared um, times small v minus b equal to RT. So instead of PV equal to RT, it is this equation where the smaller case v is nothing but the actual volume divided by the number of moles. Here A and B are constants and they are different for different gases. Okay, so the relationship is different um, for um, real gases between pressure, volume, and temperature. Now, what is the other difference? Um, Presence of intermolecular forces, both attractive and repulsive. And the third difference is such gases can undergo condensation or liquefaction. They can become liquids. Okay, so there is a phase change property for such gases. So this is some important point to consider. Now, another thing to understand is the differences between the three states of matter. The difference between the three states of matter primarily arises because of the intermolecular forces. In solids, the intermolecular forces are really high. So the energy that's stored in each molecule, or in the energy stored in a solid uh, due to the energy within its molecules, is divided into potential and kinetic energy. And that's the case with all states of matter. Okay. However, if you check the distribution of energy between potential and kinetic, in solids, the potential energy dominates. Okay. That's mainly because they have strong intermolecular bonds and that restrict their motion. Okay, so most of the energy is stored in these bonds. They do have some vibrational, so if you heat a solid, the molecules start vibrating and it stores energy more and more in their vibration modes. It's hard for the molecules to move around and translate. So they're in fixed positions, more or less, and they vibrate around that mean position. But as you keep heating, the frequency and amplitude of that vibration changes, and the stored energy increases in the kinetic side. Eventually, the kinetic energy gets higher and higher, that a lot of intermolecular forces are broken, and the intermolecular forces become weaker, and the solid melts to become a liquid. Okay, now the kinetic energy has components in translation. These molecules can move around. So it can move here, bounce around. It can travel everywhere within the medium. So it becomes a liquid, as opposed to just vibrating in one place earlier. It can also rotate. It can also vibrate a little bit. As you further heat, now the translational motion is the main kinetic energy. Okay, there's very little intermolecular forces and very high translation motion. Now, if it's a real gas, the intermolecular forces, sorry, if it's an ideal gas, these intermolecular forces become really negligible compared to the translational portion of the energy. Okay, so this is what happens when phase changes. So when the gas condenses and becomes liquid, it gains vibrational motion of molecules within the liquid, which is almost non-existent when it's in the gas state. Okay, it also gains a little bit of rotational energy, which is also very little in this case. And then it also is close enough to other molecules that the intermolecular forces are coming into play. So it gains a little bit of potential energy. If you further cool it or compress it, it becomes a solid. Okay, so the liquid freezes into a solid. So these are the three states of matter. In this lecture, we are primarily concerned between the liquid to gas phase transition. Okay. Now, the same thing that we just described can be plotted on something called a phase diagram. So phase diagram is basically a graphical representation of the three phases that we just discussed, solid, liquid, and gas, under varying temperature and pressure conditions. Okay. So increasing the temperature has a tendency to take everything towards translation energy. So you're basically increasing the temperature, uh, basically takes everything towards the direction of gas. Okay, you're breaking the bonds, um, reducing the potential energy, and storing all the energy into translational motion. And um, that is what the tendency is, as you can see in the phase diagram. Okay, so increasing the temperature takes it to gas phase. Now, increasing the pressure has a tendency to take the substance towards its liquid state. Okay, you could see in terms of this is water's phase diagram, and the one on the left is air's phase diagram. Um, so you can see that as the temperature increases, the tendency is to go towards gas or vapor, and as the pressure increases, your the tendency is mainly towards going to high intermolecular forces or high potential energy. So it is mostly as a liquid, okay, and a combination of low temperature and high pressure would keep it as a solid. It usually don't happen with air so much. Air doesn't, there's no solid air. Um, Even getting the air to liquefy, you're talking about extremely cryogenic low temperatures at which it can stay as a liquid, okay, and at high pressures too. Now, what are the typical normal temperature ranges that you see your outside air in? It's way outside this range. It's, let's say we are talking normally, when we talk about the temperature conditions in a room, it's in the range of 25 degrees C. So it's almost always gaseous phase for air, and it's far from the two-phase region, okay, from the phase change region. So the molecules have so much energy in terms of so much translation energy in term compared to um, the intermolecular force of attraction in the case of air, that it could be mostly considered ideal gas under standard conditions. Okay, it's way far away from the phase transition region. Okay, it is the intermolecular forces are much negligible. On the other hand, with water, you can see these are typical temperatures that we see um, in real life in within a room, and it's very close to the phase transition region, okay, under normal conditions. And typical normal pressure in atmospheric pressure is somewhere here, okay, 101 pascals, kilopascals. So under most normal conditions, it's really close to the phase transition region. So water vapor typically um, has real gas behavior, okay, especially close to this line where this transition happens. So the mixture of air and water, a lot of times we can deal with them as an ideal gas and use ideal gas relations, but closer to the region where it's close to phase transition, in such situations we have to bring in the real gas considerations. Okay. Another interesting thing to note here is, of course, increasing the temperature, you're increasing the translation motion of the particles, and increasing the pressure, you are increasing the intermolecular forces. Eventually, when you keep increasing both, you'll reach a point. So you're increasing in pressure and you're increasing in temperature. Imagine you're pulling this from the right and also pulling it from the up. You'll reach a critical point after which it's not liquid and neither a gas. Okay. So it has the properties of both liquid and gas above this critical point. So if you look at within this rectangular region above that, or in this right corner, it behaves both like a liquid and gas. Okay, so it has really high density here, like a liquid, but at the same time, it will like if you put this substance in a container, it will fill the whole volume, so it will diffuse like a gas. If you pour a liquid into a cup, it will stay in the bottom, right? In this case, it is behaving like a gas and a liquid. It has very high density, like a liquid, and it will dissolve materials into it just like a liquid would. And at the same time, it will act like a gas where it will fill the whole volume. It will diffuse uh, within that volume just like a gas would do. Okay, so critical point is for water is somewhere close to 374 degrees C and 22,000 kilopascal. Okay, and the same for air is happens at a much lower temperature, but the pressure is really high. So um, this is not related to this lecture, but something to know about when you look at the phase diagrams. There is also this triple point within the phase diagram where all of these three phases coincide. Okay, that is um, all the three phases are very close to an equilibrium. So a water vapor could directly go into ice here. At the same time, it could also become uh, liquid, um, depending on whether you're increasing the pressure or the temperature. Okay, so that's a point where it's where all these three lines merge. What are the gas laws relevant to psychrometry? And by psychrometry, I mean the humidity. You've heard about the relative humidity percentages. There are other terms within humidity, like saturation pressure, um, absolute humidity, things like that. So to determine all those variables and all those parameters, and I will talk about those 9 parameters in the next slide, typically we have to use both the ideal gas relationships and the real gas properties. So the ideal gas relationship, for example, PV equal to nRT, a good way of um, using that is, so the pressure, let's say you have a total pressure um, in a box, then the pressure of air, and if you have only air in there, the pressure of that dry air can be assumed to be determined by the temperature with this equation. Now, if you replace the box with just water vapor, the same relationship. So you could assume that if there is nothing else, only water vapor, there is no liquid water, it's purely water vapor, you can assume that it's also an ideal gas. Okay, as long as there's no liquid. The moment there is liquid, that means we are exactly on this line, that you have both water and vapor. Then we could not use the PV equal to nRT equation. Okay, if it's pure vapor or pure gas and there's no trace of liquid in it, then we could determine the pressure of that particular gas, either dry air or water vapor, using the equation of ideal gas law. Now imagine both are present in that volume. You have some air, dry air mixed with some water vapor, which is what normally all the air around you is. Um, Almost all the time there is some amount of water vapor in the air. In this case, the total pressure inside this chamber is the sum of pressure of dry air plus the pressure of water vapor. And each of them can be individually determined by the number of molecules of each is present. So individual PV equal to nRT equations could be used, and that could be used to find the total pressure. Okay, so total pressure is the sum of partial pressures. This is another ideal gas law, and it's called Dalton's law of partial pressures. So if you have two gases and they have certain number of molecules within the same volume, then total pressure is the partial pressure of first gas plus the partial pressure of second gas. And each partial pressure is proportional to the number of moles of that particular gas. Okay, so you're using these two ideal gas principles for estimating the properties of um, moist air. Now, if you're close to this region where you have to account for the gas or the vapor liquid equilibrium, then you cannot use the typical um, ideal gas law anymore. Here you have to look at the phase equilibrium laws, and you're looking at the saturation pressure formula. And the saturation pressure formula comes from the Clausius-Clapeyron equation. Okay, and it is an exponential relationship with temperature. The relationship of pressure to temperature is exponential. Okay, so it's not a straight line, as you can see, and you will be able to plot this in Excel yourself once you learn how to use CoolProp. You can see that the relationship between um, pressure and temperature along the saturation line is not linear, it's exponential. And that's the case for air, and that's the case for water. Okay, and it's somewhat similar to this equation. Okay, in this case, the value of L is the latent heat and latent heat of vaporization, and T is the absolute temperature in Kelvin, and P naught is basically a reference pressure that you choose. Okay, so this is a real gas relationship because ideal gases do not have latent heat of vaporization. They do not have phase change. All right. So what are the 9 properties that are important when it comes to psychrometry? The first 3 of them are related to temperature. There's something called the dry bulb temperature. It's basically the temperature. If you stick a temperature sensor um, inside this any of these chambers in the air and not in the liquid, okay, whatever temperature you measure is the dry air temperature. Okay, it does not account for evaporation of moisture. So you're just putting that thermocouple or the temperature sensor in a chamber, and the chamber could have some moisture in it, some liquid in it, um, and the temperature sensor should be away from that liquid in the gas phase. The chamber may not have liquid, but just have moisture in the air. You could still measure the dry air temperature. The chamber could have no moisture at all. In all these cases, whatever temperature you're measuring is the dry bulb temperature. Now, wet bulb temperature is the temperature measured by a thermometer with a wet wick. So the temperature sensor is purposefully made wet. So typically you'll add a wet wick or cloth, and then you will either blow a lot of air onto it and try to evaporate, or you will swing this thermocouple such that the water evaporates, and as the water evaporates, it will keep dropping the temperature of the sensor until it reaches a steady state value. That particular temperature is called the wet bulb temperature, okay? And we'll describe that more later on. Since it involves the evaporation of the liquid in the wick, it is related to the real gas behavior because it involves phase change, right? Uh, the third temperature is the temperature at which air becomes saturated and the water vapor condenses. Okay, so if the temperature in a chamber drops continuously, at some point the liquid in the air will start to condense. That particular temperature is called the dew point temperature. Okay, if you're not bringing additional air from outside or additional moisture, you're only reducing the temperature of this closed system, and at some point the gas starts to condense on the surfaces, then that temperature is called the dew point temperature. And this particular calculation requires usage of real gas behaviors because, again, there is a phase change. Now, what is relative humidity? Relative humidity is usually expressed as a percentage, is the ratio of the actual water vapor content to the maximum water vapor content the air can hold at a given temperature. So if you have a box with uh, some air molecules and you start adding some water molecules to it, if you keep adding at some particular uh, amount of water vapor added to it, it will start condensing just like a dew point without changing the temperature, right? It will start condensing. So that particular scenario is RH is 100%, okay, when it starts condensing. Anything related to that, like if you have half the amount of water compared to what will cause it to condense, then you have 50%. Okay, if you have 3/4 that amount, then you have 75%. So it's related to what is the maximum that the amount of water vapor that can be in that particular air or in that particular system with, without condensing. Um, that is the relative humidity. Okay, so the ratio of the amount of moisture that is currently there in that system to the maximum amount that will cause condensing, um, or the minimum amount that will cause condensing, above which if you add further, it will keep on condensing. That ratio is the humidity, relative humidity, expressed in a percentage. Again, this is based on real gas behavior of water vapor. What is humidity ratio? Humidity ratio is also described as specific humidity. This is the ratio of mass over mass, okay? How many grams of moisture is present in a kilogram of dry air, okay? So let's say you have zero point 0.1 milligram of water in this 500 gram air, okay? So how many grams will be there in 1,000 gram air? So you do that conversion, find that ratio, and that value is the humidity ratio. It's the ratio between the mass of air that is present in that chamber and the mass of water or water vapor that's present in that chamber. Okay, so that ratio um, expressed in grams per kilogram. Okay. Now, what is absolute humidity? Absolute humidity is not like relative humidity. Relative humidity is related to the max humidity and it's a percentage. Absolute humidity tells you the exact amount of water for a given volume of air. So it's the mass of water vapor in a given volume of air. So if you suddenly collect a certain volume of air, if you know the absolute humidity of that room or that location, if you know based on that okay, I will have this many grams of water in there. So it's basically grams per meter cube. Okay, it's almost like the vapor density um, of water within that volume. Density of humid air is nothing but if you take a certain volume of mixture of air and water, whatever the mass or volume of that particular mixture is, that's the density of humid air. Okay, so it includes the mass of both the air and water vapor and the total volume of the combined system. Another important thing is the partial pressure of water vapor. And most of these calculations are based off of partial pressure. Okay. And this is the important concept that you need to learn, how to determine partial pressure of water vapor for a given temperature. And once you know that, everything else is derived based on that. Actually, I should go one step uh, further. Um, the most important thing that you should be able to determine is actually the saturation pressure. Once you know the saturation pressure, you back calculate the partial pressure, and from then on, everything else is easy to determine. Now, the saturation pressure um, is directly related to temperature. Okay, if you look at this line, okay, this line, this is the saturation pressure temperature line. So for any given temperature, saturation temperature, there's only one corresponding saturation pressure. Okay, so there's no multiple pressures or multiple temperatures. It's just one line, one curved line, or one curve. So if you know the saturation pressure, you can determine the saturation temperature and vice versa. And you could easily do that using the CoolProp or other property calculating software. All right, so some of these, like I mentioned, some of these properties are calculated based on real gas behavior. Some of these are calculated based on um, ideal gas. So in case of saturation pressure, because it's accounting for the transition between vapor and liquid, again, it's based on real gas. The partial pressure is based on the fact that um, the pressure is a based on the molecular or the molar distribution of the gases within the system. So it comes from Dalton's law of partial pressures. So the partial pressure of water vapor is based on the ideal gas behavior, primarily based on the ideal gas behavior. All right. Now let's further look into the temperature versus pressure relationship when we only have gas and there's no liquid present, and we are talking about ideal gas. In the situation with water vapor and air, whenever you have no liquid present in your volume, you could potentially treat it as ideal gas, okay? And what I mean by that is if you do this PV equal to nRT, especially when there's no condensation, there's no liquid anywhere, if you plot pressure versus temperature, and if you try to extrapolate all the way back, all of them would converge towards this 0 Kelvin. Okay, and they are basically lines. And this is true for just water vapor and air mixtures. And you can do that study in CoolProp and verify that. The moment we are considering, let's say your temperature and pressure combination created a condition where there is some condensation, then you're away from the ideal gas zone and it's not ideal gas anymore. So if you take 2 points far enough in pressure and temperatures and then create the line, you should be able to replicate the ideal gas behavior even with a mixture of air and water vapor or either of them alone. Now consider a moist air mixture. Um, so like I mentioned earlier, in the case of psychrometrics, if you don't have any two-phase present within that uh, gas volume, whether it's a gas mixture or a pure gas, it's okay to use the ideal gas assumption because you're slightly away from the two-phase region, and there's no condensed water in these cases. So let's take a particular volume that's shown here, um, and this is a air water vapor mixture. Let's say we have a pressure sensor here. Okay, that pressure sensor will be measuring a total pressure value. Um, for the sake of argument, let's say it's measuring um, close to 100 kilopascals. Okay, and if you remove all the and let's say you have a temperature of 25 degrees C. Okay, these are just assumptions. Now, if you remove all um, the blue molecules here, which are, let's call these water molecules. Okay, if you remove the water molecules and you only have dry air and the temperature is still 25 degrees C and the volume is still the same as before, now this sensor might measure a pressure that is lower than this 100 kilopascal. And let's say it's measuring 95 kilopascal. Okay. And all the removed water molecule you put in another chamber. Okay. And the same volume, and it's at same temperature, 25 degrees C. So it will measure close to 5 kilopascal. So if you add these two, 5 plus 95, you'll get the total pressure. So this is basically the law of partial pressures. Okay. So the total pressure in this volume can be thought of as a combination of pressures coming from air and from water vapor if they were assumed to be occupying that same volume, which is the most important thing here. The volume is same volume V, assumed to be occupying at the same volume and the same temperature. Then the sum of those pressures will give you the total pressure. Okay. All right. Now, what happens with a mixture of um, vapor and liquid? In this case, a mixture of water and water vapor. Now, this pressure sensor, I should say one more thing. So in here, if you took the temperature and pressure here and started to plot it, okay, you will get a straight line when you increase the pressure and temperature. Or if you increase the temperature, the pressure will increase as a straight line, right? And if you interpolate, it will go to 0 Kelvin. But if you did the same thing here, okay, you will not get a straight line. You will get this saturation curve based on the Clausius-Clapeyron equation that you saw earlier, right? So as you increase the temperature, the pressure is not only dependent on the increase in molecular motion, okay, when the molecules move, they hit each other. So basically, the pressure is nothing but collisions of molecules on the walls of this chamber, right? So as the molecules um, collide, the pressure increases, which is what happens in ideal gas. But in addition to that, a lot of molecules, extra molecules come out, right, due to phase transition. Um, and because of that, you have an increase in number of molecules and also an increase in collision. Okay, so the increase in pressure is faster for the same increase in temperature in case of a two-phase mixture. Okay, so the pressure will raise much faster for a small change in temperature when you have two-phase because of the evaporation of the water molecules. And note that there is no air here. This is all water, okay? This is all water. Now we have to use this line in figuring out what happens in case of a mixture with air and water, okay, which is the normal air that we see outside. All right. Before I go one more step, um, you need to understand that so far I have been talking about evaporation, okay? Evaporation and condensation. What is boiling? So boiling is when this pressure that we calculate here, this pressure is equal to the atmospheric pressure. Okay, let's say the atmospheric pressure is somewhere here, 100 kilopascal. Okay, 101325 Pascal at sea level. Okay, at that point, let's say you're heating a cup of water or a bowl of water. At different temperatures, it will have different pressures right above it. Okay, and there will be a lot of air around it too. So there will be air molecules and then water molecules are coming out. So as you get closer and closer to this point, now the pressure of water vapor here matches the actual surrounding atmospheric pressure. Okay, so it's no longer a small fraction of the total pressure. Now everything above this water surface is all water and it's fully close to atmospheric pressure, and it starts changing phase not just at the surface but also from all over the liquid. Okay, so that's what boiling is. So boiling is the rapid vaporization of a liquid when its vapor pressure equals the surrounding pressure. Phase change can happen throughout the liquid volume, and bubbles can form inside the liquid during boiling. So, like I mentioned, once it reaches the boiling point, liquid can become gas anywhere within the liquid. Okay, so it's close to the boiling temperature, you add a little bit more heat, and wherever that heat gets added, the phase change happens right there. Before that, it was evaporation and it's mainly happening at the surface. Okay, it's just the molecules are leaving just the surface here. Phase change can happen throughout the liquid volume and form inside the liquid during boiling. Now, if it's just to drive home the point, if the liquid column is really tall, okay, and it's close to boiling point, phase change will happen wherever the pressure is not too high, because if there's really a deep column of liquid, the pressure may be too high here. But wherever the pressure is close to the boiling pressure, it will start bubbling from there on. Okay. All right. Now let's get to the first moist air parameter, which is the relative humidity. So what is relative humidity? Now let's first consider a particular case where relative humidity is 100%. Okay. Um, if you look at only the blue molecules here, okay, and you remove all the air molecules, which are the red, and you imagine another chamber, okay, partially with liquid and partially with vapor, and only consider the vapor volume, then this and the air, the water vapor present here, they will have the same number of molecules. Okay, so if you add one more molecule here, it will start condensing because it's already, if you add one more molecule here, it will start condensing that to liquid too. So this scenario is both of them are exactly on this two-phase line. Okay, they're both on this two-phase line. For a given particular temperature, you add one more molecule, it will become liquid. It will go to the left in both these cases. So when somebody says that the relative humidity is 100% in a room at temperature 25 degrees C, what they mean is the condition of the moisture is exactly at 25 degrees C point on the saturation line. Okay, so let's say there's a 25 degrees C line here. Any little change would cause it to move towards liquid. Okay, any little further addition of moisture into the air will start causing condensation. So what would be the pressure of water at this scenario? You can easily figure that out based on the pressure temperature relationship on the saturation line. Okay, so that's a known function. At 25 degrees C, there is only one pressure for water under uh, uh, there is only one pressure for water at which it will have can occupy as both liquid and vapor. That's the saturation pressure. Okay, and it's the same pressure that will be there here. So the water pressure here is same as the saturation pressure that is calculated at this condition at 100% humidity. Now, what do you mean by 50% humidity? That would be the 50% of that pressure that you calculate here. So the pressure of water vapor is same as the saturation water vapor pressure. So let's say at 25 degrees C, the saturation water vapor pressure is 3,170 Pascal. Okay, that's an actual value. So the pressure of water vapor in a 25 degrees C room at 100% humidity is same as that saturation pressure. At 50% relative humidity, it will be half of that pressure. Okay. And this, if you count the number of molecules, let's say there's n molecules here at 100%, at 50%, it will be the number of molecules at 100% divided by 2. Okay. It's just that ratio. So the number of blue molecules here would be half the number of blue molecules here. All right. So that's relative humidity. So this is basically where it comes from. Like I've a lot of times people would say that the air cannot hold more water. Um, so if you add one more molecule of water, the air cannot hold it. It's not that the air cannot hold it. Okay. In this case, there's no air. Okay, there's no air. It's the same type of box. It's just the saturation property of water. Okay. If you add one more molecule of water, the collisions in the gas phase would drive one extra molecule back to the liquid phase. Okay. It cannot be accounted for in the vapor phase. It generally has nothing to do with the air molecules around it. Okay. All right. Now, the next one is humidity ratio. For the same conditions we discussed about 25 degrees C saturation pressure, humidity ratio is the mass of the blue molecules to the mass of the red molecules, which are uh, air molecules. Okay. And you can see it's these two numbers. And it's not exactly half. This is not exactly half. At 50%, it's not half of this, even though the pressure is exactly half. Why is it not exactly half? Because if you reduce the water molecules to half to create the same total pressure here and here, okay, the temperature is 25 degrees C, and the total pressure here and here, you have to add some more air molecules. So the air molecules have increased and the water molecules have decreased by half. So effectively what happens is humidity ratio will decrease more than half because the air molecules have increased, okay? All right. Now, absolute humidity. Absolute humidity is basically talking about the mass of water molecules within a given volume. So that's pretty straightforward. You can easily calculate based on the properties of saturation properties here and here. So once you know the saturation pressure and saturation temperature, it's easy to calculate the density, okay? Both the vapor and the liquid. So these are all standard calculations. So you could easily calculate the density of saturated water vapor. Um, and once you know that, you know the basically the absolute humidity. Absolute humidity is almost the same. Um, it has the same units as density. Okay, so what happens when you go from 100% to 50%? So 100% you calculate you based on the density at saturation, right? To calculate the absolute humidity. Um, at 50%, you have to just multiply it by the 50% ratio over 100%. So it will be just half. So this value is just half of this. Okay, exactly half. The number of molecules is less, so the density goes exactly half. Number of molecules half, so the density is half. So that's absolute humidity. Now, how does absolute humidity change um, when, for a given volume of air, when there's no condensation or evaporation, how does the absolute humidity change as you keep changing the temperature? The answer is absolute humidity doesn't change because the number of molecules is the same, so the density has to be the same. What changes is the relative humidity. Okay, the reason for that is if you increase the temperature, you can see that the um, partial pressure of water vapor changes considerably from the previous partial pressure, and the corresponding saturation pressure of water vapor also increases considerably. So the ratio of the actual water vapor pressure to the saturation pressure decreases when the temperature increases. So the relative humidity decreases. Okay. If the temperature decreases, it goes the opposite way. The relative humidity increases. In all these cases, the absolute humidity is the same. The humidity ratio changes because of the change in the um, number of air molecules to account for uh, the constant total pressure. Now, moisture density is basically the density of humid air, right? So mass of air uh, and water vapor per unit volume. Now, assume you have dry air, and then assume that you have moisture with different humidities, relative humidities. Assume they're all the same pressure, same total pressure, okay? And same temperature. So for in this case, 30 degrees C. So assuming they are the same pressure, which is, let's say, atmospheric pressure, as the relative humidity increases, the density of this moisture decreases. The reason for that is the number of molecules, when they're remaining the same, air molecules are replaced with water molecules, and water molecules are lighter than air molecules. Okay, so because of that, the overall weight for a given volume decreases. So the density of humid air is lower. So humid air will uh, rise to the top, and dense air will fall to the bottom. All right. So the next thing to look at is the dew point temperature. And we'll look at how to calculate all these values in the next lecture, but let's try to understand what exactly dew point temperature is. is the temperature at which air becomes fully saturated with water vapor, or 100% relative humidity, okay, when cooled at constant pressure. So let's say you're operating in a room where there's no condensation yet. Um, let's say you're operating at some condition here, at some temperature. Okay, these are not exactly meaningful temperatures. Let me draw a different one here. So let's say you're in a room and the room's temperature is such that the water, so this is the water phase diagram, okay, especially the liquid vapor interface, okay, and assume that the water condition of the water vapor is in the gas phase at that temperature. And if you cool that room, what will happen is you'll go in the direction towards left, and at some particular temperature, it will start condensing. So you'll reach the saturation temperature for a given pressure if you start cooling. Okay, so that condition is called the dew point temperature. Dew point. So as an example, consider this um, box with 30 degrees C temperature and a mixture of air and moisture, and the relative humidity is 50%. In that scenario, the partial pressure of water is um, is this particular pascals. Okay. Now, if you keep cooling on one wall or one particular section of that chamber, okay, you'll slowly start noticing water condensing there. The temperature at which the water will start condensing and becoming a liquid film or liquid droplets, that particular temperature is the dew point. If you raise the temperature above that, there's no chance of condensation. Okay, so why does that happen? If you consider just this region locally, the condition within where it's condensing will be similar to a two-phase region. So this is 100% humidity in this region, not everywhere else. Everywhere else is 50%. But in a small region here, the temperature is very close to 18.45, and the rest of it is, let's say, 30 degrees C. So within that small region, the conditions are similar to what happens on the saturation line. Okay, so the pressure is the same as the pressure everywhere else within here. So let's say the pressure is 21, 23 Pascal, and the uh, temperature for that particular Pascal for two phase is 18.45. So it's similar to this region on the two phase diagram um, in this particular local condition. Okay. Now, if you cool all the walls everywhere, you will see condensation occurring everywhere, all along the walls. So this is what happens when um, you see some local condensation, where the condition in the whole room may be warmer, but locally you're getting close to this two-phase region on the water's two-phase diagram. Okay, and we'll discuss more on that when we actually calculate dew point using CoolProp. So a lot of examples, dew on the leaves in the morning because the leaves are colder in the morning, potentially due to the radiative heat transfer in the night that the leaves get colder, and in the morning the water condenses on the cold surface because locally it is close to the 100% relative humidity due to low temperatures. Okay, and you can see if sometimes refrigerators, the insulation is bad, the surface gets colder and you see condensation. If you take a Coke bottle from the refrigerator and put it in a humid room, the surface of the bottle is cold and locally it can condense there. Okay, several examples like that. Okay, now let's try to define wet bulb temperature. Consider a closed chamber. Okay, no um, mass transfer or energy transfer to outside, so closed insulated chamber. Okay, and you have a certain temperature inside. Let's consider that temperature to be 30 degrees C, and let's say the initial relative humidity is 50%. The corresponding pressure of water for that temperature is this particular Pascal. Okay. Now, what is the dew point temperature? Sorry, what is the wet bulb temperature of this system? To estimate the wet bulb temperature of this system, where you have vapor water or water that's present as vapor and that water that is also present as liquid, you assume that more liquid vaporized, okay, and you reached a condition of close to 100% humidity, okay, it vaporized and now it will not vaporize anymore, okay, because it's saturated, okay, so it reached a point of 100% humidity. Then what would happen is, because it's a closed system and there is no heat exchange to outside, the temperature of the air will drop, because that's the heat that is being used to help the water to evaporate and become water vapor. Okay, so that drop in temperature and the final temperature that this particular closed chamber achieves is the wet bulb temperature. Okay, now at this particular temperature and this particular humidity, the number of molecules present in that particular volume would be same as that we discussed earlier about the two-phase diagram. So if you look at the two-phase diagram, the particular temperature that is, for example, 22 degrees C, it will have a pressure corresponding to 2645 pascals. Okay, so it will be right exactly on the saturation line. So if you focus only on the water molecules here, it looks almost identical to the number of molecules, and the pressure will almost be identical to the pressure of a fully water system or water vapor system. Okay, all right. So that's the wet bulb temperature, and the same thing could be measured. You could measure it another way here. So initially you measure it with a dry bulb thermometer, and then you install a wet bulb thermometer with a wick, and then you sling it in this room and it evaporates, and it will evaporate until it no longer further evaporates. It reaches close to 100% humidity around, not everywhere within this room or within this chamber, but just around the sensor. The humidity gets closer to 100% and it doesn't vaporize anymore, and that temperature will also be close to 22 degrees C. Okay, so either way you'll be able to figure out the wet bulb temperature level. All right, so this is an example of two thermocouples or two temperature sensors attached to one measurement device, which will help you measure both the wet bulb and the dry bulb uh, temperature values. So in this case, you have to first make this wick wet by adding some water to this. Okay, once it's wet, you take this whole thing into the room in which you want to measure both the wet bulb and the dry bulb, and you sling it or rotate this, okay, by holding that in your hand. So it has a dry bulb thermometer, wet bulb thermometer, and a sling mechanism. Also a wick or a cloth that can be moistened with water. So the principle is of evaporative cooling. So if you hold the handle and sling it for some time, and it will quickly drop in temperature because of evaporation, and then it will reach, so the temperature, this is time, and the dry bulb temperature will be constant, let's say, dry bulb. And the wet bulb thermometer initially will start the same and it will quickly drop and it will reach a steady state value. Okay, so this is the wet bulb value and this is the dry bulb value. Okay, so using these two values, you'll be able to figure out the relative humidity of the room. Okay, um, and why does the two values differ? It's because of evaporative cooling. If the two values don't differ, if both the values are exactly the same, T dry bulb and T wet bulb are exactly the same, that means humidity is 100%. There is no evaporative cooling possible for the wet wick. Okay. So another thing to notice, lower the humidity. So at 100%, they're exactly the same. As you lower the humidity, they try to deviate. Okay, dry bulb will be different from wet bulb. So lower the humidity, larger the temperature drop on the wet bulb and larger the temperature difference between the two. Okay. Now, how do we calculate relative humidity based on these two? Um, I'll show you how to do that in the next lecture using CoolProp. But normally what people do is they look at the psychrometric chart, which is shown here, and you have an axis for dry bulb temperature, okay? And you have the lines that correspond to that dry bulb temperature. And then you have a curved axis for the wet bulb temperature, okay? And there are lines that correspond to that, these blue lines too, right? So then wherever they intersect, you have to find what is the humidity value, which are these red lines, red curved lines. The ISO humidity values are going up, relative humidity values are going up. So if they intersect exactly here, for example, at the top, that means the humidity is almost 100%. Okay, the dry bulb temperature is same as the wet bulb temperature. So when they intersect here, the humidity is 100%. If let's say they intersect at some other point here, then in this case the humidity is 60%. Okay, so basically you try to find the intersection point and look for what the relative humidity is. You can also figure out humidity ratio, okay, and at times you can also figure out in some charts you can actually figure out absolute humidity also. Okay, all right. Now we've discussed psychrometric parameters. Where are psychrometric principles or psychrometric processes needed, or when do we need it? Why do we need to study it? Every time you're talking about any process that involves air with moisture in it, and you're talking about heat transfer or uh, energy related processes, you have to account for the amount of moisture in the air. Okay, so anytime you're doing this kind of process, if you don't account for the relative humidity, you will get errors. Okay, primarily. So if you're doing sensible heating, which is just heating without any condensation or evaporation, but the presence of moisture will change the heat capacity of that system. It will change the density of that system, etc., etc. So you do need to know um, what is the actual humidity. If you're doing sensible cooling, just cooling with air, then also you'll need some knowledge about psychrometry. And whenever there is any amount of condensation or evaporation, you definitely need to know psychrometric principles, because without that you don't know when exactly water will start
to condense or what will start to evaporate when you vary the other parameters in your process. One thing to note here is in most of these conditions, most of these variables are changing. The dry bulb temperature, wet bulb, relative humidity, humidity ratio, absolute humidity. They're most of uh, the time they're all changing. They're all changing, especially when there is a phase change. So these are all phase change processes, right? In here, they are all always changing. If there is no phase change, just heating and cooling, the absolute humidity and the humidity ratio, they remain constant. Okay, and the wet bulb temperature also remains constant during just no when there is no phase change. Okay, and which direction they do, whether they increase or decrease, is explained in this chart. All right. Now I wanted to give you one particular example of uh, that is not exactly directly related to um, any of these processes, but it's related to an actual application in a refrigerator. When you have French door refrigerators, where there are two doors that open left and right like that, they usually seal on something called a flipper mullion. The gaskets seal on this flipper mullion. Okay, so this mullion is exposed to a lot of cold air, so you can easily get some condensation on its surface. And this is an example. So inside that there is a heater. Okay, there's a heater in the back behind the surface, and this heater turns on or off based on a sensor that measures the temperature and the relative humidity of the room. And this temperature is the dry bulb temperature, okay, because it's not measuring any evaporation. So based on what the sensor does, the heater will turn on or off to make sure that this surface is above, T surface is above the dew point, okay. The dew point is calculated based on this temperature and relative humidity. So how much heat is needed to make sure that it's above the dew point uh, is usually determined experimentally by varying these two variables, okay, dew point and humidity. And they do that so as to make sure that they don't consume a lot of power to employ the heater. They want to just use enough heat to be slightly above dew point so there is no condensation. If you always heat with a high load, you might be inefficient and you'll consume a lot of energy under all conditions. So only when the room's humidity is high, for example 90%, and the room is also warm, 29 degrees C or something, then the heater might function a lot more as opposed to when it's 20 degrees C and let's say 30%. Okay, so the heater will be basically having an adaptive control. So this is an example of knowing psychrometry and understanding of temperature, relative humidity, and dew point, understanding the science to solve an actual practical problem. Okay. All right. In addition to this, I would like you to check out some online calculators. For example, this one, where you can calculate a lot of humidity parameters online. So you can put a reference ambient pressure here. You can put in a dry bulb temperature, for example. I'm going to put 28, relative humidity of 50%. And if I run calculate, it's going to tell me what is the absolute humidity, wet bulb temperature, and a lot of other points. Okay, so under this condition, if I cool it to 16.6 degree, it will start condensing because that's the dew point temperature. Now if I increase this humidity to 100%, let's see what happens to wet bulb temperature, right? Calculate. Okay, it's giving an error. Let's take it to really close to 100%. Let's say 99.7. Oh, that's not the problem. Let's give it 100% here again. and calculate. So when you give 100% again, you can see that the wet bulb temperature matches the dry bulb temperature. Okay, so at full humidity, the wet bulb temperature is same. Now, if it is 0%, they should have the max difference. Okay, it should be really cold here. Okay, I probably need to put some small amount of humidity value. Okay, you can see that if the relative humidity is really low, then the wet bulb temperature versus the dry bulb temperature, the difference is really high. Okay, all right, so check out this calculator. We will create our own calculators using CoolProp for calculating all these parameters. All right, thank you.